This episode is a bit crazy, but we are among us. Don't tell anybody else. We want to know whether we, I mean you or me, could communicate to the next solar system or even further. And if so, could we transfer images from ourselves so that extraterrestrials get an idea how we look like? Today we have a rather unusual agenda. We will talk about extremely big distances and the associated wave propagation loss. Alpha Centauri is only one example among others. We assume that we will send out radio messages to an alien civilization on another planet far out in space, just like on the picture here. I will briefly explain the math behind, which will allow us to estimate the technology needed to overcome the distance. It will be really interesting to analyze which range and transfer rates we could achieve using today's technology. We need to understand the physics of wave propagation. Since the universe is an almost empty space, we can assume that waves propagate like in free space. By the way, I need to mention that I published 2 earlier videos about terrestrial wave propagation. From the episodes number 15, 16 and 17, my followers know how to deal with wave propagation. The mentioned tools are still available to download for the episodes mentioned. But anyway, here are the important equations to understand this. The first equation is telling us that for a radio link, the so-called system gain needs to be greater than the path loss. The second equation is a handy engineering formula for the path loss, which we apply. Our system gain is given by a longer equation because there is a number of measures which we can take to improve it. As usual, we need to consider transmit power, receiver sensitivity, and the antenna gain of the transmitter as well as the one of the receiver. Now, in addition, we can consider the gains from a number of transmitters and receivers which are working in parallel. Furthermore, we can consider the gain from a number of repeated transmissions. The receiver sensitivity is limited by the internal noise figure, as the first equation is telling us. The internal noise power is 4 times Boltzmann's constant times the absolute temperature in Kelvin times the frequency bandwidth delta F. I'm dealing with this here because the receiver sensitivity can be significantly improved by cooling down the receiver front end. Finally, the radio noise level in dBm is given by the last equation here. Now, with the presented equations, you can compute the theoretical maximum range of radio waves in free space where they just can be detected. Okay, in a practical case there is, however, noise from our Sun or from other stars that needs to be considered. Astronomers may forgive me that I'm simplifying this in the following. Now it's time to do some computations. We got a tool here to help us a bit with the calculations. It helps us to estimate whether communication is possible over astronomical distances. Okay, Here are now the distances which we are talking about, and we already calculated the associated wave propagation loss. We have the distance in kilometers, astronomical units and in light years here. However, it makes no sense to deal with tremendous kilometer numbers here. We simply hide the two columns so that we only see the distances in light years. It is notable that the resulting propagation path loss figures given in dB are still values which we can handle. However, of course, the corresponding linear propagation loss factors are also tremendous. The path loss is frequency dependent. In case we choose 145 MHz, we get 187 dB path loss to the Moon, 230 dB to the Mars, and 279 dB to Voyager, which travels now already 30 years long, and it just left the solar system. Even when this was a challenge to achieve, we can take these radio links as proven. But how is about the next solar system, the Milky Way, or even another galaxy? Knowing the path loss, we can calculate the signal strength in the distance in column M here. For the maximum path loss, all gains mentioned before are considered. The corresponding parameters we can adjust on the right side in column U. In column N, we have the receiver sensitivity calculated from the absolute temperature and the bandwidth. We can adjust the parameters here in the upper section. In case the sensitivity level is lower than the received signal level, a radio link can be established, at least in theory. Unfortunately, in practice, the receiver's inherent noise figure is not the only source of disturbing radio noise. Besides man-made noise, the so-called cosmic microwave background, which is an effect of the Big Bang, which we still receive today, there is a strong radio noise in our frequency band from the Sun and other stars. We need to consider this here. In columns K and L, we have an estimation of the radio noise level of our Sun and other stars. As a reference, we use the radiation in this frequency range that arrives on Earth from our Sun. In this calculation, the distance to the star and the antenna size is considered. Now, what are the colors telling us here? When we change our parameters, the results in columns K to M will change accordingly, and we indicate whether a radio link is possible using the green color. The range can be restricted either by radio noise from the Sun or other stars, indicated by the yellow color, or it can be restricted by the receiver sensitivity, which is then indicated by the red color. Okay, now we are coming closer to the answer of our big question. Can we send a message to Alpha Centauri or even further? I will explain now two examples. In a first example, we look at a theoretical experiment using amateur radio equipment. In the second example, astronomers' high-tech is applied. For the amateur radio case, we use the frequency 435 MHz. The receiver temperature is 293 Kelvin, which corresponds to 20 degrees Celsius. The radio channel bandwidth is 3000 Hz and the applied transmit power shall be 100 watts. The antenna gains of the transmitter and the receiver side shall be 16 dBi. The number of digital modulation levels shall be 16. Besides the channel bandwidth, it defines the transfer rate, which we didn't discuss yet. Applying all the parameters, we find that the Moon can be reached even with a reasonable transfer rate. So this would be nice for ham radio if somebody would live on the Moon. Can we increase the range now? A cheap measure is of course simply to repeat the message 1000 times. The receiver could integrate the repeated signals and separate it better from the radio noise. The measure is setting back the transfer rate, however Mars can be reached then. The pretty slow transfer rate would allow text messages, pictures would take days to be transferred. Next we try 10,000 repeats, which seems not sufficient to reach the next level. Then we motivate 10,000 amateurs to synchronize in cooperation, and with that we can cover the whole solar system. Now the transfer rates are getting almost unbearably slow, and considering this effort, the range seems to be a bit disappointing. Now we do our utmost we can think of. We motivate 1 million radio amateurs on Earth and 100,000 on the receiving side, which of course is highly questionable if any alien civilization would do that. With that we can reach Alpha Centauri and a few other stars. Alternatively, our signals could be received in that range with an Arecibo category space observatory with 61 dBi antenna gain, operating at 50 degrees Kelvin, which appears more likely to happen. Okay, having in mind that the response time for the signal to travel forth and back would be between 8 and 20 years, it seems not the biggest issue that you can transfer only about 10 megabytes per year. In such time frames, it would allow to transfer pictures indeed. But look at the tremendous effort and look at the cost estimate on the bottom that are just derived from the cost of the electricity consumption. 140 million euros to send out just 1 megabyte. For the second example, we try to understand what an astronomer's high-tech equipment could do here. We choose the frequency to 700 MHz. We can consider a receiver operating at a temperature of 50 Kelvin and a bandwidth of 100 Hz. For the high-tech stuff, we can probably assume a higher number of modulation levels. We remain at 16 here. Then we start with 10 kilowatt transmit power, 50 dBi antenna gain, which corresponds roughly to a 50-meter dish antenna. On the receiver side, we choose 20 dBi. With that parameters, it is no problem to cover the solar system. Next, we choose 10 megawatts. 50 dBi on the transmitter side, 50 dBi on the receiver side, and 10 repeats of the message. And with that, we reach Alpha Centauri, even with a reasonable transfer rate of about 80 bits per second. Next, we apply 1000 repeats, and a few more stars are getting into reach. However, the transfer rate is down to less than 1 bit per second. Next, we use 10 transmitter sites, and some stars are coming into reach. 10,000 repeats and 10 receiver sites would reach many more stars, and if we would do our utmost with 100 megawatt transmit power per transmitter and 100,000 repeats, we would reach structures corresponding to a single-digit percentage of our Milky Way at a ridiculous slow transfer rate of 30 kilobytes per year. But okay, when the response time is up to 20,000 years, you can take your time to send out messages. In this case, even a few years. And more than 400 billion euros to send out 1 megabyte is really over the top, isn't it? Our insights. The good news is that with a worldwide amateur radio community interworking, we could, in theory, reach Alpha Centauri. But the bad news is that experts believe that there is no life possible in that solar system, and it seems impossible to get to the next level with that technology. Not even with a really high number of cooperating amateur stations. With astronomers high-tech on the transmitter and the receiver side, we could reach a distance of 1000 light years and more, which is a mind-blowing amount of kilometers. In the far distance, the transfer rates would be very slow. So, there you have it. We can answer the initial question. Yes, we could send a message to Alpha Centauri, and with high-tech even further. However, we need to keep an eye on the time for reply that we can expect. For Alpha Centauri, it would be already 8 years. In case we reach many other stars, we could expect a response only after 200 and up to 2000 years. Okay, we could cover a spectacular range with our signals in space. However, for a conversation, the traveling time of the radio waves is more critical than the technical range. And on a galactic scale, our technical capabilities are still pretty short range. We only can reach a single-digit percentage of our own galaxy. From a wave propagation point of view, I summarize the following. If we would ever receive a signal from the far distance, I mean 10,000 to 10 billion light years, then there must be a species which is able to control natural radiation sources like radiating stars, black holes, etc. for their communication. As promised, this episode was crazy and a bit complicated. Hope you enjoyed it anyway. And just to remember, in case this video is sent into space, I am the one living in the outer range of the Milky Way on the third planet in a solar system around a shining star called Sun. Now stay tuned and don't forget to subscribe and support the channel. See you soon in the coming episodes.